Good day, everyone. I'm going to present you a work that I made with Yuan Kang Lu, Pol Grasland, and Guy Cloutier about the generation of shear waves in soft media in two regimes, ablative and thermoelastic regime. So there are a number of concepts which have been already introduced earlier in the summer school, so it's good because I had to change a little bit my presentation, but this way it is a little bit shorter, so we can go to the lunch earlier. So I'll just give a few words about elastography. It has already been presented by Remy and etc. So just briefly what I need for the presentation. Okay. The elasticity of biological tissue varies a lot among tissue, especially the shear modulus. So the shear modulus corresponds to the deformation of a tissue when there is a strain, a force applied perpendicularly to the solid. And this modulus varies a lot among most biological tissue. So this is a parameter that many people try to measure. So to measure this parameter, there is one physical concept which is interesting. It is a propagation of displacement inside a solid. So in an infinite medium, displacement can propagate either as a shear wave or as a compression wave. The compression wave, you see the scheme here, is just a displacement which propagates like this, if it is plane, and if it is a compression spherical, it's like this. We can see it on the scale. And there is also the shear wave, which propagates if it is a shear wave, plane wave like this, and if it is a spherical wave, it is a small rotation. So the interesting thing is that the shear wave propagates at a speed which is equal to the square root of the shear modulus divided by the density. If we assume that the density of the body is the same almost everywhere, we only have to induce a shear wave somewhere to measure its speed to map the elasticity of the tissue. And this is the base of the shear wave elastography. So in shear wave elastography, we induce shear wave, we image the tissue. Right? From the images, we try to calculate the displacement. And if the displacement propagates as shear wave, we can compute the elasticity from the shear wave speed. And yeah, so the shear wave imaging technique can be MRI, ultrasound, OCT. There are other techniques like photoacoustic, but it is not highly developed right now. So yeah, this was a summary of things which has already been said during the summer school normally. So just to sum up, in the shear wave elastography, we induce a shear wave, and this can be done with an external shaker, with a focused acoustic wave. I have shown a few years ago that we can also use electromagnetic field. So if we combine an electrical current and magnetic field, we can also create shear waves. There are other ways which are under study to induce shear wave, but these are the main one. And could we use a laser to induce a shear wave? So this is the main question of this presentation. So we have seen this morning with a glorious presentation that in metals and such solids, it is something known that we can induce compression and shear wave in such materials. But in soft solids like biological tissue, it is not so evident. So some related work, there is photoacoustics. Photoacoustic relies on the emission of a laser inside the biological tissue. When the laser is absorbed by a structure which is highly absorbing, there is a dilatation of this inclusion, and this dilatation creates some elastic wave, some acoustic wave. So acoustic wave can be acquired by acoustic probe placed all around. But in this case, the acoustic waves are only compression wave. It is due to two main facts. First one is a question of frequency. The frequency of the acoustic waves which are created are more or less around the megahertz. Compression wave at the megahertz can propagate over a few centimeters, but shear waves at the megahertz can propagate in less than, doesn't propagate, it propagates in less than 1 millimeter, even less. So even if there was shear waves, they wouldn't propagate very far. And the other thing is due to the geometry of the inclusion. Most of the inclusion are more or less spherical. And if you have a spherical inclusion which dilates, you can see on the small GIF here, it gives more compression than shear. So we have compression wave and not shear wave. So there is another work which has been presented 2 years ago. A team has proposed to use a laser to induce surface acoustic wave, and surface acoustic wave are not exactly shear wave. It has been presented in details this morning. But a team has proposed to apply a laser inside a thin wall, bladder wall. It creates surface acoustic wave, and they have tracked the surface acoustic wave with OCT, so they have been able to measure the elasticity. So the experimental apparatus that I have done to know if we can induce shear wave with a laser is shown here. So it is quite simple. There is a laser beam which emits a laser beam which is emitted in a sample here. The sample was observed with an ultrasound probe to measure the displacement inside the sample. And from the ultrasound probe, from the ultrasound images, we can calculate the displacement and find if there is any shear wave. So the sample was a gelatin phantom, and there is something important inside. There were some graphite particles. The graphite particles allow to have some speckle in the ultrasound image. So speckles the small dots here. So we could make some. So we could find the displacement inside the phantom. And also the graphite particles were there to absorb the laser beam. If not, if there was not any graphite particles, the gelatin is transparent, so the laser beam will be transmitted without being absorbed. So from this experimental apparatus, I have seen this. So here you can see the displacement inside the sample along different times. So 1 millisecond, 1.5 millisecond, 2.5, 3 milliseconds after laser emission. So what we see is that there is a displacement which propagates as shear wave inside the tissue. From the speed of the shear wave, it is 5 meters per second. We are sure that it is a shear wave. Its central frequency is 500 Hz, and the maximum displacement amplitude is quite low. It is 0.02 micrometer. If we increase the laser beam energy from 10 millijoule to 200 millijoule, we see a displacement map pattern which looks alike to the previous one. But if you really look carefully, you see some differences. So I've sketched most the main difference. Here you have a displacement, initial displacement to the left, and here you have a displacement to the right. So either from directed toward outside the medium or inside the medium. And also, if you really look carefully here, you see 3 L cycles, so a blue cycle, red cycle, and a blue cycle, and here you can see only two of them. So there are slight differences, but it shows that the regimes to create the displacement and the shear wave are different depending on the laser energy. So we have made an analysis, physical analysis, and we have proposed a thermoelastic at low energy, which is more or less identical than what we have seen this morning in the photoacoustic imaging. So the model supposes that we have an initial optical intensity I0 given by this formula, and this optical intensity decrease along depth with an exponential decrease. There is a gamma, which is the absorption coefficient of the medium, and in our case we have measured it and it is 40 micrometers. So we have measured this by taking different slices of thickness of the medium, and we just measured the amount of light was transmitted. So this was to calculate the absorption of light in the medium. Then we can calculate with the heat equation the increase of temperature in the medium. So when the laser beam was emitted, this term, the spatial variation of temperature, is negligible compared to the other one. So during laser emission, this equation can be simplified like this, and we can calculate the maximum increase of temperature due to the light absorption of laser. And a numerical calculation of this equation gives that we have a maximum increase of 3 Kelvin at 10 millijoules. 3 Kelvin, it is quite low, so it is compatible with thermodilatation principle. Then I wanted to calculate the displacement which was created by in this model. So we have adopted a one-dimensional model. So as the depth of absorption is something like 40 micrometers and the beam diameter was 5 millimeters, the depth of absorption is 100 times lower than the diameter. So, and this justifies this approximation. So if we calculate the stress at the surface of the medium, the stress is the sum of the axial strain and a coefficient which is due to the thermal expansion. If we make a small assumption that the first Lamy coefficient is higher than the second Lamy coefficient in biological tissue, and if we see that the stress is equal to 0 at the medium surface, we can have a simple formula to calculate the displacement inside the medium. And if we calculate the displacement, we find something almost equal to 0.025 micrometers, and it is very close to what we have measured experimentally. So that justifies the physical model that we have adopted. We can go a little further by making by trying to calculate the displacement pattern due to the thermoelastic expansion. So here we cannot have a one-dimensional model, we need at least a two-dimensional model. And the thermoelastic expansion was modelized as two opposite forces perpendicular to the medium surface, and the other displacement were the other forces were negligible compared to the two opposite forces. So we had a matrix here along space and time, which represents the amplitude of the force. And there is a big equation here, the green function, some of you are familiar with it, which allows to calculate the displacement at one point, given a point force in the middle of the matrix. So simply the displacement along space and time is then the convolution matrix between the green function, so the function above, and the matrix of the applied force. So this allows to calculate the displacement along space and time, and this is given here. And what is really interesting is that we find the initial displacement, which is directed outside of the medium, as we have seen experimentally here. And we also see the three half cycles, so the blue, red, and blue cycle here that we can see here. So that was the physical description of the thermoelastic regime. And now we can see the ablative regime, which is at higher energy. So the temperature and absorption of light is the same as previously. So just the main difference is that the increase of temperature is about 60 Kelvin. So at 60 Kelvin, we are closer to a vaporization temperature of the medium. If we approximate the medium to water, it is close to the temperature of vaporization of the water. So the model that we have adopted is that we vaporize a part of the medium. So some particles are ejected outside the medium, and by reaction there are some displacement inside the medium. It's similar to if you fire a gun, there is something which is ejected, and there is a reaction to the displacement. So again, we can calculate the stress, which is the sum of the axial strain and parameter which shows the ejection of particles. This term corresponds to the energy which is brought by the laser divided by the energy which is needed to increase the temperature of the particle to the vaporization point, and then to change the state of the medium of a liquid to a gas to be ejected. And we can again make a little assumption, and so we find the formula for the calculation of the displacement. And finally, it gives a displacement of almost 3 micrometers, which is again very close of what we have measured experimentally. So by making the same step as previously, we have modelized the force as a force towards the medium, and the side forces are negligible compared to the main forces here. So we can have a matrix of the applied force that we convolute with a green function to have the displacement along space and time. So and the results are shown here. We can see again the displacement here, which is generated inside the medium, like as we have seen experimentally, and we only have two cycles here, as was seen experimentally. So just to have all the maps on the same slide, here are the main result of the simulation and the experiment, and we have a good correspondence between the numerical analysis and the simulation and the experiment. So we wanted to see the transition between the two regimes. For that, I have taken the displacement, theoretical displacement, and we can remark that the displacement is proportional to the energy at low energy, and at high energy here it is proportional to the square of the laser energy. On the right here you can see a plot of the displacement function of the laser beam energy in a log-log scale. So at the low energy we have a slope of 1.05, so it means that there is almost a linear relationship, and at higher energy we have a slope of 2.18, so a quadratic relationship. And this is exactly what was predicted by the theory. So
how do you change the energy of the laser?
It's the parameter in the laser that we could change from 10 to 200 millijoules.
So the laser near the image, you have the way of changing the time domain? Or?
The time domain, no, it was fixed. It was 10 nanoseconds, but the energy which is emitted at each pulse, we can control it. There is just on the panel. Yeah, we can just choose from 10 to 200 millijoules. That's why there are 20 points, because it is 20 energy that I have access to. So everything until now has been done in a phantom, and I made another manipulation. That experiment that I would like to show you is in a biological sample, an eye, a pig eye. So there is a laser here which is emitting a laser beam inside the pig eye here, So it was going through the eye and was absorbed on the retina. And there was an ultrasound probe which was acquiring the ultrasound image a long time. As it was a high frequency ultrasound probe, we could only have the upper part of the eye. And on the right you can see the ultrasound image of the eye. Here, so at the beginning there is nothing. And when the laser beam is emitted, the whole image is blind. We are blind because of the compression waves which are emitted by the phenomenon. And then in color you can see displacement, positive and negative displacement, which propagates through the eye here. So we can measure the speed of this displacement, and the speed is something like 3 meters per second, and it gives an elasticity between 15 and 40 kilopascal, which is in agreement with the literature. So the most obvious remark of this work is that is it safe to do such an experiment? The answer is no. We shouldn't do it clinically. In fact, the energies was something like 5,000 times higher than the standard, the maximum permitted energy. So it was just a small manipulation, but we couldn't apply it on biological tissue. So for skin, this was in eye. For skin, we could use higher energy laser. But in the experiment that I've shown you, the minimal energy that I've used was 10 millijoule, and it is still higher than the maximum permitted. So we should decrease the energy to measure, to make some elastography measurement. But the problem is that at low energy we have very small displacements. So if we decrease the laser energy, it will be hard to measure displacement and to have reliable results. So there are different ways to solve this problem. I've seen two ways to solve it. So we can apply a productive layer on on the organ that we want to study. If we put some black paint or a varnish or something like that, we can emit the laser beam on the black paint. This way the laser beam will be absorbed by the paint and not by the tissue. So the tissue will be protected. But in practice, if we can access to the organ, maybe we don't need to make non-invasive imaging. And another way to solve this problem would be to use higher spatial resolution device like high frequency ultrasound or OCT imaging, because if this would allow to measure very small displacement, so we could use a lower energy laser to measure the displacement. With OCT in particular, it could be very interesting because we could use a laser to create the shear wave and a laser to track the shear wave and to make elastography. So it could be a way to have a 100% laser technique to measure elasticity. So yeah, we are arriving at the end of this presentation, so thank you for your attention.
Thank you very much. Any questions? The ultrasound system that you use, so it samples at, it gets images at 1 kilo, so fast?
Yeah, I didn't detail it, but yeah, it was ultra-fast imaging, and I had images at even 2,000 images per second. So
is that like what is used in a? It's not like what is ordinarily used in a hospital. It's more.
In hospital, I don't think that they are using ultra-fast imaging in hospital right now, but it is going slowly. It is being adapted slowly. I don't know if people know if it is used, but I think that in hospitals they are still using slow ultrasound imaging.
And OCT can be as fast?
OCT can have a high frequency, can be up to kilohertz, can acquire data at 100 kilohertz. Yeah, but it's still under improvement, OCT, but yeah, it can be as fast as ultrasound imaging.
Yes, there are ultra-fast scanners in hospitals since 2008, but it's not the majority of the scanners yet.
You mean
in the future, all the scanners will be ultra-fast.
You mean the FibroScan one or
the Explorer?
Explorer?
Yeah.
Okay.
And the displacement was only 0.02 micrometers,
Yeah.
which is much less than a pixel of the camera,
Yeah.
but still with correlation techniques.
Yeah, in fact, it is quite lower than the spatial resolution of the ultrasound, and but this is due to the fact that we track displacement, and even if we have a displacement which is lower than a pixel, we can find this displacement.
It's like a digital image correlation.
Yeah. In fact, we interpolate the shape, local shape, and we can see very small shapes. But in practice, for elastography, we try to have a few micrometers of displacement to have a reliable displacement. So, in ultrasound elastography. So, the 10 millijoule results are have too low displacement to be directly applied in ultrasound elastography.
So you're detecting ultrasound with ultrasound.
No. Because the shear wave are low frequency, it is not.
You're detecting audio with ultrasound. Yeah.
So you mentioned the focusing was a few millimeters
The focusing of
the laser.
the laser was not really focused.
Because if you want to generate shear waves, I guess you need to have diffraction. So you need to have focus of the source.
No, here the laser was not focused. It was a 5 millimeter beam, and it was absorbed by a small volume, as I described.
Can you show an image where you see the acoustic shear wave propagating? Like this.
Yep.
This one, for instance, on the right side image, it's like a spherical wave that propagates.
What wave?
Spherical.
Yeah.
3D wave.
Yeah.
And the wavelength seems to be like 5 millimeters.
Yeah, something like that.
So it's roughly the size of the laser beam.
Yeah.
Okay, so the frequency or the wavelength from the acoustic wave you generate is imposed by the focusing of the laser.
Yeah, in fact, I didn't explain why do we have exactly this central frequency of 500 Hz. I'm not sure for now what gives the frequency of the shear wave. I thought it was due to propagation of the temperature of the heat inside the medium, but I'm not really sure. It might be due to the size of the laser.
I think you impose the wavelength by imposing the size of the lateral size of the laser beam. If you would focus it, you would generate higher frequencies.
Okay. I have tried with focused laser, but I didn't remember to have seen any difference on the central frequency, but I have to take a closer look.
Okay, so my question was, another way to get shear wave would be to have a change in the symmetry somewhere.
Yeah.
Maybe, and some people did it with crystals cut off axis.
Okay.
So you have symmetries, crystal symmetries that are tilted, and you shine this material, and because it's off axis, you will generate planned shear waves.
Okay, yeah, that's true that we have to find a way to have, as you say, a non-symmetrical way to produce the displacement to have the shear wave. That's why if we have a spherical inclusion which dilates, there will be only compression wave almost. And yeah, but if we have a non-homogeneous laser beam or non-spherical inclusion, maybe we could get also some shear waves. Yeah.
In your Cornea experiment, you actually show us a video saying that there are shear waves. Actually, with OCT, which is measured is the surface waves, right?
Yes, yeah. Yeah, in fact, it is not really a shear wave, it is a lump wave, so a sort of surface acoustic wave, and yeah, it is not exactly a shear wave. I presented this result to show at least one result in a biological tissue, but it's not exactly shear wave, yeah. Yeah, shear wave are only in a bulk inside in an infinite medium, and yeah, here it is obviously not a bulk, it is more a thin layer, and the physics is different for thin layers. So